Okay. Got it. Okay, now we are live. Good. We can start. I have a double. Okay, welcome back to these webinars. Sorry, but I will hear. Sorry. I have to stop this. Okay, welcome. Okay, now I don't hear myself. Good. So welcome back to these seminars. It's a series of virtual seminars. We started 31 of January with Vidal Munoz, and today we have Federico Stefanini from the Department of Environmental Science and Policy. Just a few words about his background. He's a statistics. He works actually on probabilistic graphical models and Monte Carlo computation. He just joined our department. He was in the Computer Science Application University of Florence, Department of Statistics. And he just joined in 2021 our department. Our seminars, you can find the all the scheduled seminars on our website, on the virtual seminars. They are recorded as well, so if you want to watch later, you can do. And today, it's a pleasure to have Federico here. The title of his seminar is Estimating Causal Effects in Cell Transformation Assay. Please, if you have questions, you can write in the chat or make just a hands up, and Federico can answer, of course. Thank you so much to be here with us.
Thank you, and welcome everyone, and thanks to Professor Laporta, Caterina, for the invitation to present my work on cell transformation assay. It's a great pleasure to be here with you, and welcome everyone, and thanks for attending this presentation. I have to share my screen, so let's see. Can you see the screen?
Yes, very well.
Great. So let's start from the very start of cell transformation assay. The ability of a chemical substance to induce cancer is called carcinogenic potential. In 2019, Federico M and co-authors stated that thousands of chemicals remain untested for their breast carcinogenic potential. And the lack of wide testing holds in general even today. So no wonder that in vitro fast and cheap assays are important in cosmetic, food and pharma fields as a first step to probe the carcinogenic potential of substances. Here we are. So cell transformation assay are a group of in vitro techniques that correlate quite well with the rodent bioassay. On the left, you see the experimental unit, rats. The study with rats lasts for 24 months, and daily checking is performed on mortality, morbidity, tumor onset, features, and so on. In vitro techniques, in particular the cell transformation assay, is based on a petri dishes. You can see in this slide one petri dish, and you count the number of fully transformed foci, these dark spots in the petri dish. This study lasts for 5 weeks, 4 to 5 weeks, and no daily checking is required. So in particular, the experimental units are petri dishes seeded with immortalized cells. So it is worth noticing that in vitro assay fits Russell and Birch 3 Rs, reduce, refine, replace, for a more ethical use of animals in scientific research. They are less expensive and quick to do, and therefore more widely adoptable. Here the timetable of a typical cell transformation assay. The experiment starts with seeding petri dishes using immortalized cells, and for 48 hours, treatment takes place with the candidate carcinogen, and then the recovery step starts, and finally, after about 5 weeks, fixing, staining, and microscope observation close the experiment. And in particular, you see magnified one focus, which is made by clonal cells growing piled up in a thicker layer with irregular boundaries. And so this is how we recognize that this clone of cells is a type 3 focus. The outcome is the number of fully transformed foci, called also type 3 foci, at the end of the experiment. We have a minimum of 10 petri dishes at each dose level. And those levels are 5 or more because the first one is a negative control. So we are talking about water or vehicle for the substance. Then we have the no observed adverse effect level, for France called NOAEL, the median lethal dose, and some other intermediate dose levels, although 5 or 6 dose levels are typically the number of levels we consider. What about the statistical analysis? Well, it's important to mention the ECVAM's expert group, the paper from ECVAM's expert group in 2012. They started with 2 families of distributions, Poisson family and negative binomial family, so that under dispersion is taken into account. But under dispersion was not addressed, and therefore they also proposed to transform the observed number of fully transformed foci, variable y, into a new variable w, which is called the Nishiyama transform of the original count. Then, by assigning a normal distribution to w, they were able to take into account the possible underdispersion. But unfortunately, in my experience, the Nishiyama transform can work quite badly. In one case study, I obtained an estimated probability for the event number of foci less than 0, so an impossible event, a probability larger than 0.19, which is a huge probability. And this is a critical point, for example, if you use predictive distribution to impute missing values. And so in year 2018, together with my former student, Giulia Callegaro, we proposed a different class of model by associating a parameter pi ik for dose level I, count k, to each possible value of variable y. And we impose some smoothness by assigning a normal distribution to the logarithm of the ratio pi ik over pi ik minus 1. So we were able to take into account for possible underdispersion, overdispersion, as well as smoothness. But now the point was, what about inconclusive evidence? Replicates of the same cell transformation assay in different laboratories sometimes provide inconclusive evidence. So what does it mean? That huge differences in averages turns out to come from the same experiment. So we have kind of pseudo replicates. In particular, the same chemical is tested, the same dose levels are considered, the same recipe is followed. The number of cell passages from the primary cell culture is the same. So why should we obtain so different averages? So Stefanini and Magrini in 2021 proposed a model for the data generating process of cell transformation assay. But before providing some details on this class of models, we need to introduce some tools useful in our discussion. In particular, directed acyclic graph. And we start with an example. Please consider three random variables, YF, YV, and YS. The number of fully transformed foci, the number of viable cells, and the amount of fetal bovine serum. The joint probability density function is everywhere positive, and then we can obtain a factorization, for example, in YV times YS given YV times YF given YS and YV. And we can represent this factorization using a directed acyclic graph where labels FVS refers to random variables. Oriented edges here indicates which are the conditioning variables of a given node. So I will use the term parent variables and child variables to indicate where the oriented edges start from and where they end. So for example, in this first DAG, we can see V and S parent of node F. And this is a way to indicate the factorized joint distribution. YF given YS and YV times YS given YV times YV. So one of the advantages of directed acyclic graph is that we can also indicate or represent conditional independence relationship. For example, look at this factorization, YF times YS times YV. So here, the joint distribution is factored in marginal distribution. And so those variables are marginal independence. And I can appreciate this feature because no oriented edge is present in my DAG. Other interesting configuration on the left and the middle, we see two chains, and on the right, a fork. Once more, for example, on the left, S is going into F, F is going to V. So the factorization is YS times YF given YS times YV given YF. YS and YV are not marginal independent, but when we condition on YF, they become independent. Another very important configuration is called inverted fork on the collider node F. And so we see S goes to F, V to F, and S and V, or more precisely, YS and YV, are marginally independent. What is counterintuitive in a way is that after conditioning with respect to F, the two variable YS and YV becomes dependent. So the message, the take-home message, is that in large networks, it's difficult to judge who is conditional independence by who. But using theorems like the disseparation theorem of Pearl and Verma and the separation theorem for undirected graphs by Lauritsen and Dewitt, we are able to judge if a subset of random variable is independent with respect to another subset given a third subset of variables. And so we can work with the structure hidden in a joint distribution. Well, after we have a DAG, we are ready for a probabilistic model. So the question is, how can we define a directed acyclic graph? Well, we can exploit the knowledge and information taken from experts, or following a Bayesian approach, we define a score function. And so using genetic algorithms or simulated annealing, we search in the space of candidate DAGs for the best directed acyclic graph. We are talking about conditional independence, so no wonder that statistical tests are useful to find a DAG suited for a data we collected. Well, anyway, after defining the DAG, we need conditional probability density functions, eventually discrete density functions. And so for each node, let's say node Vi, we have the probability of node Vi conditioned on the parents on Vi. And once more, the expert knowledge is very important, and some data analysis based on experimental or observational studies is useful. And we want to use the bias rule for updating our information. I understand this is a very brief sketch. Full account of the approach can be found in Kohler and Friedman probabilistic graphical models. I did not even try to cite all the literature. Tons of contributions are very too much to describe. This is a list of my small contribution, but I'm not going to talk about this today. So what does it mean to follow the Bayesian paradigm? Let's say we have defined a biological context, psi. We define a model by means of a DAG, and the conditional distributions associated to each node depends on parameters. So theta is the vector of model parameters. We collect data, capital D, and we ask to expert about the degree of belief associated to the vector of parameters. And so we define the initial distribution, the so-called prior distribution of model parameters. Well, if we are able to define the likelihood function, which is in short the probability of the data that we observed given parameters and the model that we specified, then we are ready to update prior beliefs to obtain the posterior distribution of model parameters given data and the model specification. We can also obtain predictive distribution, which are useful not only in forecasting, but also for missing data imputation. Well, right now, we spoke about a statistical association, statistical distribution. And so this is about what we observe in a given context. But we are also interested in experiments. Scientists are interested in the experimentation. And so we should distinguish passive observation, I mean the distribution of values for variable epsilon in the population among individuals showing x equal to small x and z equal to small z. So this conditional distribution refers to a population, but when we condition on x and z, we are restricting our attention to a subset of the population. I'm just observing a system, a process, and this is a quite different activity from active intervention. And so Judea Pearl proposed to distinguish the manipulation, the intervention of the system using do x equal to small x in the conditioning part of this formula. So here the distribution of y in the population is of interest if everyone had their x value fixed as small x among individuals showing z equal to small z. And so we understand that these two conditional distribution may or may not be the same. This is the point. And well, let's spend a couple of minutes to make the structural causal model of Pearl formal. We have the collection of endogenous variables explicitly related within a DAG, V1 by V2 up to Vk. We have exogenous variables, that is an explained background condition from U1, U2 up to UK, and the set of deterministic function H1, H2 up to Hk. And so Hi defines the value taken by the variable Vi given the value of its parents and the exogenous variables. So each node is associated with one exogenous variables besides one or more, or eventually none of the endogenous variables. A causal graph make this relationship explicit. And now we need just a joint distribution on the exogenous variables to define a probabilistic causal model. So a couple of remarks. When the exogenous random variables are marginally independent, we can work with the induced random variable that are with the induced distribution of the endogenous random variables, so V1, V2 up to Vk. And among the remarkable results obtained by Perl and co-authors, we have an approach for the evaluation of mediation effects. So is it important to distinguish a probabilistic model from a causal model? I think yes, because consider a simple DAG in which V goes to S and V goes to F. And let's plot in this illustration S on the axis, F on the y-axis, S on the x-axis, and you see a linear relationship between S and F. So the question is, should we recommend the intervention S equal to 47, so manipulation, in order to increase the value of F? Apparently, the linear relationship says we should, but when we manipulate S, the DAG says that F will not change because it does depend on V and on its exogenous variables. And so why we see the linear relationship? This is a matter of random variable V. The sample space of V is made by 7 different values. And so when we condition on V, you see a subset of points that is without any particular shape. So from the causal point of view, the linear relationship is a sort of artifact because we neglected to consider the variable V. Another important example is on the collider node F we talked before. Assume for a moment on the left that we receive the first chunk of data from the whole experiment, and it is characterized by all units having F in the interval 54.75. And so the first judgment is this is a straight line relationship. But after we wait for all the data arriving to our lab on the right, we see that S and V are marginally independent. And we already stated the same results before. So the straight line relationship is due to the data selection process restricting the sample size space of F. Okay. So we now are ready to formulate a first hypothesis about inconclusive evidence. So we imagine that differences in fetal bovine serum among batches is present, and differences due to clonal variability are also present. And this may happen because fetal bovine serum contains a lot of important substances like growth factors, which are known to enhance cell replication and possibly transformation. Clonal variability might also explain differences observed when inconclusive evidence occur. And so here we have a first DAG in which dose level of the candidate carcinogenic substance goes into A, the number of viable cells in a Petri dish, goes to T, the total number of foci in Petri dish, and goes to F, the number of fully transformed foci in each Petri dish. S stands for fetal bovine serum and C for cell batches. But actually, right now, we consider today one lab cell transformation assay in which S and C are constant, and therefore our working DAG is just made by nodes D, A, T, and F. Okay? Okay, and so we are ready for presenting our parametric Bayesian specification of this model. I stands for dose level DI, J for Petri dish J, theta is a vector of model parameters. And so given the factorization specified by the DAG and assuming the conditional independence relationship among variables in different Petri dishes at the same dose level, but also at different dose levels, we can factorize the joint distributions as here expressed. And finally, we are able to describe all the observables by means of statistical distribution, as I said before. Going into details, for example, we considered a generalized logic function of the original number of viable cells after transformation. And such a log ratio is assumed to follow a normal distribution with the parameter mu A and sigma A. Another example, the total number of foci is assumed to follow a discrete distribution where counts, the sample space of counts is from 0 to 50. This is a discrete distribution based on the kernel or the normal kernel. And so mu t is the location parameter and sigma t is the scale parameter. I stands for dose level and J for Petri dish. Oh, well, we decided for 50 as the largest number of foci that we can count in a Petri dish because the size of a Petri dish is quite limited, let's say 8 to 10 centimeters. Finally, we have the number of fully transformed foci distributed like a binomial distribution with phi I, the parameter representing the probability of full transformation. Tij is the total number of foci at dose level I in Petri dish J. It's time for elicitation. For the elicitation, we are Bayesian, and well, our expert is not one of the Simpson scientists shown here on the right, and I can't disclose gender or name, but I can say that our expert has 15 years of experience in bulb C3T3 tests of genotoxic and non-genotoxic substances, either sampled from the environment or from pure stock of chemicals. So the expert is trustable, and this is the answer I gave to a reviewer of our paper. Anyway, is already published. So under the assumption of marginal independence of model parameters and assuming that the additive decomposition of generalized logics holds, mu t decomposed as a function of A, T, and tau I, we introduce the dose-dependent transformation rate tau I, and then we work with some algebra that now I'm going to skip, and we define the whole model. Well, after the elicitation takes place, we revised the elicited beliefs by inspecting the marginal distribution of observable quantities. For example, on the left, you see A, the number of viable cells in Petri dish after treatment. And you see that the conditional box plot show exactly what we expect. The negative control is dose level 1, very close to the initial, the distribution is very concentrated on the initial nominal value of cells in one Petri dish. And the last one on the right, dose level 5, show a box plot where the median is exactly half the original, the starting number of cells in a petri dish. And this is LD50, by the way. So we now take the structural equation for the number of type 3 foci, starting from this equation and working to the definition provided by Pearl and earlier by Robbins. We define, after some algebra, the total effect of those level I with respect to the negative control, the null, which is phi I times the expected value of t under di minus phi null times the expected values of t under d null. This total effect, you can see, depends on five parameters as well as on the total number of foci. And this is an important point. Let's give a look to the natural direct effect. This is defined by phi I minus phi null times the expected values of t under the null. And then we have also the natural indirect effect at those level di, which is phi null times the difference of the expected value of t at the two reference concentrations. So a couple of remarks. If the expected number of the total number of foci is equal at di at the null, then the difference is null, and therefore the natural indirect effect is as well null. In that case, the total effect and the natural direct effect are equal. And another remark, if we have a large t, then we are able to better estimate phi I and phi null. And so the difference that is the key factor in NDE is better estimated. So how can we use the model we just defined for solving the problem of optimal sample size? So first of all, why we decided to use NDE? Well, only type 3 foci cause tumors when injected into mice, but large values of T increase the expected values of F, and therefore the total effect is not, in our opinion, the best candidate. And so our expert decided the target for this sample size determination.
Una domanda di Angelo.
Oh, oops. Is someone asking? No.
No, was someone with the microphone on. Don't worry.
Okay, no problem. So the expert decided for an expected value of the total number of foci equal to 4, difference between phi's 0.125. The implied natural direct effect is equal to 0.5. And the uncertainty about the estimates of the natural direct effect can be quantified by building a 95% credibility interval, the Bayesian equivalent of confidence intervals, and quantifying the difference between endpoints of this interval. So L21 is just the highest endpoint minus the lower endpoints. And the expert decided for 1/3. So the goal is to find the smallest sample size able for an NDE equal to 0.5 to perform estimates with uncertainty equal to 1/3. So the solution to this problem was obtained in 2 steps. The first one is to perform a Monte Carlo simulation in order to find those collection of parameter values, theta star 1, theta star 2, and so on, able to produce a natural direct effect equal to 0.5, plus minus a small amount, numerical amount. And actually, after drawing 100,000 parameters from the informative prior distribution, we just saw, we obtain 10 values of the theta vector. So theta star 1 up to theta star 10. In the second step, we perform a Monte Carlo simulation in which we draw 100 synthetic datasets for each selected parameter. So overall, we have 1,000 datasets. And we started with the sample size n equal to 10 at each dose level. We obtained the posterior distribution for each dataset. We calculated the natural direct effect and the credibility interval for such quantity using the posterior distribution. We calculated also the estimated expected value of NDE and of L to 1 using the simulated distributions. We repeated the above steps for n equal to 10, 20, 30, and 50. That's it. This is the algorithm that we developed. Couple of minutes just to say that all these simulations were executed on the Google Cloud Platform, in particular a Linux instance of Compute Engine with 16 virtual CPUs and 64 GB of RAM. When n was equal to 10, we waited 2 hours, and for sample size n equal to 50, 14 hours were required. Okay, here are the results. We have M bar, the average posterior mean of natural direct effect. Z bar is the percentage of 95% posterior credibility intervals for NDE, not including 0. And this is an important feature if you want to perform the Lindley test about the possibility that NDE is equal to 0. And W bar, the average width of the 95% posterior credibility intervals. So here we see that when n increase towards 50, M bar is going towards 0.5. No wonder that the average is not equal to 0.5 because we are using informative prior distributions, and therefore it expected that some distortion in a sense at small sample sizes. Only when the sample size diverge, unbiasedness come out. So about Z bar, we see that from n equal to 10 and above, often the null value is not included in the posterior credibility intervals, and this is a nice feature. And finally, we see that for n equal to 20, the uncertainty is 0.367. For n equal to 30, the uncertainty is 0.310. And so by interpolation, we found that the optimal sample size is n equal to 27, when the expected uncertainty is 1/3. So a couple of comments. 27 is almost 3 times the minimum recommended sample size for these experiments. But please notice that our sample size is specific for the natural direct effect. And we might have chosen the total effect if you wanted, or the indirect effect. And in this respect, other experts might prefer a smaller uncertainty, or maybe a different size and different magnitude of natural direct effect. But this is more a toxicology issue than a statistical issue. So we are close to the conclusions on this work. We defined a structural causal model and an algorithm for sample size determination that might accommodate different choices of target estimate. Although we provided some reason to prefer the natural direct effect. Well, we have some limitations in what I've just described. For example, we did not take into account for different batches of reagents or different batches of cell lines. Extensive model checking with known carcinogens has not yet been performed, and so model checking is an open issue that should be addressed in the future. We might want to revise the elicited distribution to take into account for specific features of a substance. For example, we might want to distinguish genotoxic from non-genotoxic substances. It could be also of some interest to increase the granularity of this model, moving from petri dishes to cells. But of course, molecular features like mRNA metabolites and also intracellular signals should be taken into account in such a refined model. And so we believe this is a challenging revision of our model. The elicitation from a panel of experts might provide information dealing with the different classes of substances, and so this is another point that we could address in the future. And last, I have a question. Is the magnitude of natural direct effects correlated with any useful feature pertaining carcinogenicity in humans? So, in other words, does it make sense to estimate the scale of this effect, and when we don't know if the scale may be related to something useful in humans? Because if the answer is no, then the event able to deeply alter metabolism could be the pillar on which to build another approach for the analysis of cell transformation assays. So many thanks to the community producing open source software, RStudio stand for sure, but also Python, Git, and Bioconductor. And thanks are also due to colleagues, students, and people that spend time to explain the features of cell transformation assay to me. So thanks for listening, and eventually you can see the paper I cited and I presented in this work, published in 2021. Thanks for listening.
Thank you so much. Thanks a lot. We cannot clap in real life, but exactly, thank you. Okay, open questions. I have also some questions, but later, please. People are... Marianna, do you have a question? I see your face. Looks like...
I apologize for skipping some statistical details, but I think they were enough. So maybe you might want to ask question by email or in the future after reading more details in the paper. If you want, feel free, or otherwise, please, yes, do your question now.
Because I have a question on the last point out, the last question that you point out as, so, but I want to ask maybe later if there are any more.
Maybe a question. How much, at some point you assumed a distribution shape for the prior, like normal distribution?
Yeah.
So how much your results depend on this choice?
Nice question. Well, strictly following the Bayesian paradigm, you should always use informative prior distributions in the Lindley sense. And this is what we did. We asked to the expert about the first 99th quantile, for example, and we try to choose reasonable distributions for our random variables. But I completely agree with you. There is a strong dependence on the prior we choose. Maybe this is not a very bad scene when you plan an experiment, because either you use prior information in a formal way, or you use prior information in an informal way, but you have to use prior information. And so we prefer to make such quantitative information, this prior information exploited in a quantitative way, so we know exactly in which way we use the prior information. But the dependency is indeed strong, and you see, apparently, from the simulations, the nominal value 0.5 is not the average over our simulations, although by increasing sample size, we get closer and closer to that value. Did I answer?
Yes, thank you.
Thank you for asking.
Hello, I also have one question.
Yes, please.
Have you tested this algorithm on yeasts that are dimorphic, that produce single cells and mycelium too? Because there the size is different.
Yeah, let's see if I got the question. So how we tested our algorithm to be sure that it works well? This is the question, right?
Mm-hmm.
Okay,
Yeah.
so as I said, we spend hours and hours with our expert, and to be sincere, a couple of experiments with Toluen were also considered after the elicitation. But we do not pretend that our very informative distribution is the best one for whatever the substances you might want to test. As I said in the first slide, there are about 30,000 substances not yet tested for the carcinogenic potential. And therefore, it could be, you're right, it could be that maybe 10 or 100 substances require a completely different distribution. But the point is, we worked with enough dispersed distribution to be able to accommodate, we hope, a large number of different substances. And as you see this slide 4.1.5, you see on the right, F is the number of fully transformed foci, type 3 foci. And you see at dose level 5, this box plot ranges from 0 to 50. So very heavy tails. And so this means that if a substance is able to push the number of type 3 foci close to 40 or above, well, our prior distribution, in a sense, should follow what the data will say. So they are very informative, but enough dispersed to be possibly a good choice for a wide number of substances. Thank you for asking.
Thank you.
More questions? No, I can ask you regarding to your last point, how is relevant for humans. So I don't know, I was thinking about this because the point is that this assay is in 2D, and the real life is in 3D. Because I work a lot on carcinogenesis in liver, actually, in rodents, in mice, actually in rats. And this is 3D because liver is a nice model to study this, and you see these spots in 3D. I was wondering, now there are a way to study the same process in 3D using spheroids and other stuff. I was wondering if you are doing something like that. You have some ideas on?
Thank you for this question. although I want to anticipate that I probably not able to fully answer to these questions. I'm not saying that because I'm not a toxicology, I will not answer. I'm saying that this is a very complex topic, as you described very well. And I just mentioned that carcinogenicity and transformation is a multi-step, multi-pathway procedures due to signaling, metabolites, and as you said, 3D relationship are also important. And so we wanted to propose this causal model as the minimal model you should consider while you are making a cell transformation assay. For no reason, we should stop here without revising this model if we want to move from a causal model to a mechanistic model. But the second one is a very different thing. As I said, maybe cells are experimental units. Signaling is very important, especially for the cell to grow in a clone that becomes a type 3 focus. And so, yes, this is the starting point, is not the end of this discussion for cell transformation assay. Thank you.
Thank you so much. Other questions, comments? No, I don't see any other comments or questions.
Maybe some,
Stefano.
If you could elaborate a little bit on how much this approach can be generalized. So imagine you have a situation in which you have a series of factors that you measure, like 100, and then something that you are really interested in, let's say, is this cell growing, or I don't know. So now you measure all these variables. So how could you construct a Bayesian network like this to answer these questions? So which factor or what would you need to do this? So which factors now will affect?
Yeah, in a sense that the point is that we try to move from the observational process towards a causal model, which is not a mechanistic model, as I said. But I agree with you that if you were able to simulate at cellular level, simulate the transformation process, then we could move towards a refined model, a mechanistic model, because I think the pillar of our reasoning is the cell. And so without simulating the process by which cell replicates and eventually get into a carcinogenic state, I'm not able to make a hypothesis about what to calculate.
So you need to remove the factors and then add them one by one to really be predictive about the causation. So just by knowing the amount of, suppose I imagine an experiment like this. I give you 10 factors, which I measure, and for each measurement, and I give you 10,000 measurements, and for each of the entire set of factors, no? Including the result. But now I would like to understand which factors are more important for the outcome that I'm interested in, which is growth. So can you do it, or you need, I mean, just based on the data, or you need a model?
Well, if you randomize your experiments, the effect size should of that factor should answer your question, right? So under randomization, if there is no confounding of mediators, it should work as expected. This is I mean, if you think...
Yeah, I think that's the problem, no? You never know if something is direct or not, no? So
right. As you can see in this slide, I started to pose questions, embarrassing questions, to toxicologists, because I read on a paper about inconclusive evidences, and actually fetal bovine serum is sold with the same label, but inside you may have pretty different things, and things that in some way catalyze or are able to cause big effects on the cells growing within Petri dish. And so this was my answer, but to be sincere, I was not able to find someone interested to experimentations with this kind of things. Apparently, after year 2016, the interest moved from cell transformation assay towards with bulb cells to other classes of cells and protocols. Try to open in the black box, looking at markers and other things. And so, yeah, I mean, I'm pretty sure that A comes before T, because if no cell is alive, I don't see at the end of the experiment any focus. If the total number of foci is 0, F will be 0 as well. But this is not a mechanistic model, it's a causal model. So we have mediation, we potentially found confounder between mediation AT and towards F. But then the model was simpler just for one lab, one protocol experiment. I don't know if I answered, but please ask in case I did not.
There is Giacomo has raised his hand.
Giacomo, yes. Giacomo.
Hi,
Oh, yes,
Federico.
Hi.
Thank you for your presentation. I just have a curiosity. Maybe it's not the focus of your presentation. It's not the focus of your presentation. Your DAG causal models, is there a way that you know to automatically generate the DAG or to prune it, just to try to answer a little bit in another way the question of Stefano, because maybe you have an idea at the beginning of the causality that makes that there is in your model that you assume at the beginning with your DAG. But is there some tools, some way to prune it or to change it thanks to the evidence given by data? Or
Data, right.
Okay.
Yeah, thank you for asking. I went quickly into slide 3.2, but I mentioned tons of contributions in the literature. I just tried to classify the type of contribution. You can use statistical tests. You can score a candidate DAG using your data, of course. But to be sincere, there is no universal way to find a DAG for sure without experiments based on the DAG you are investigating. So to say, if you perform randomized controlled experiments, you are in a good position for discovering causal relationship. But you know, in many ways, you are not, it's not allowed to do that kind of experiments, or they are expensive, whatever. Sometimes the intervention is almost impossible. Think about to transform a woman in a man, or vice versa. So sounds strange to manipulate some features of a process. So for one reason or another, randomized controlled experiments are not always feasible. But as Pearl said in his book, most of our causal knowledge in the history of man is not coming from randomized controlled experiments. So the point is to build an hypothesis that is finally a DAG. According to the DAG, you build experiments for probing your tentative DAG. So this is, I think, a way to go. When you use black box approaches, you sometimes, I don't want to say always, but you often end with equivalence classes of DAGs. So it means that your data are not enough for finding just one final best DAG. And so maybe you identify the top ranked equivalence class, and look into the structure inside such a class. You plan an experiment specifically devoted to refine the equivalence class you found. I mean, I love Bayesian networks, at least from 2000 years, but I do not love very black box approaches, at least in biomedical sciences. I love those approaches when you, for example, you do maybe image analysis. There are fields in which the black box approach works great. But when you want to understand what's going on, causal models give you tools for reaching the goal. Did I answer?
Thank you. Thank you, Federico.
Thank you for asking, Giacomo.
So really, thanks a lot, Federico. It was very nice, the seminar and the discussion. And so thank you so much. Thank you for all of you to be here. And let's see in the next seminar, I think in the end of February. You can check on the website. So thank you. See you soon.
Thank you, Caterina. Thank you, everybody.
Thanks a lot.
Bye-bye.
Bye.
Thank you.
Thank you. Bye.